Assalamualaikum warahmatullahi wabarakatuh. And my name is Muhammad Amir Hakim Rahman, and this is the introduction of our group project. The study of fundamental of logic serves as the backbone of discrete mathematics, providing a formal language for mathematical reasoning and a clear communication. It focuses on the structure of statement and the relationship between them. By using logical connectivity to build complex proposition from simpler one. By understanding how to manipulate conditional statement, build truth table, and apply rule of inference, we can determine validity of argument and ensure that our conclusion are based on sound variable step in the realm of mathematics and computer science. Logic is just not theoretical tool, but a practical framework used to design circuit, develop algorithm, and verify software integrity. In a real-world context, these logical principles are most visible in cybersecurity and system access control. Every time a user attempts to log into a secure platform, the system executes a series of if-then conditional statements and logical gates to verify identity. For example, a system might grant access if and only if the correct password is provided and two-factor authentication code is verified. If any part of the logical chain fails, represented by a false value in the truth table, the entire argument for granting access becomes invalid and the user is blocked. By applying the rule of inference to this security protocol, the developer can predict potential vulnerabilities and ensure that only authorized individuals can access sensitive data.
In discrete mathematics, logic is built upon proposition, statements that are either true or false. Conditional statements and biconditional statements are two of the most important ways to connect this proposition. A conditional statement is an if-then statement, denoted as P implies Q, where P is the hypothesis and Q is the conclusion. It asserts that if the first statement is true, then the second statement must also be true. Interestingly, if in logic, the only time a conditional statement is considered false is when the hypothesis is true, but the conclusion Q is false. In all of the scenarios, even if P is false, the statement is technically true. From any conditional statement P implies Q, we can derive three related statements. Converse, where Q implies P, switching the order of the hypothesis and the conclusion. Inverse, where negation P implies negation Q, negating both the hypothesis and the conclusion. Contrapositive, where negation Q implies negation P, both switching and negating the statements. A biconditional statement is an if and only if statement, written as P if and only if Q. It is much more restrictive than a standard conditional statement because it works in both directions, P plus Q and Q plus P. For a biconditional statement to be true, both P and Q must have the exact true value. If one is true and the other is false, the entire statement is false. This is often used in mathematics to prove precise definition where two conditions are inseparable. Truth table is a mathematical table used in logic to determine the truth value of a compound proposition based on every possible combination of truth value for its individual components. It serves as a visual and systematic tool for checking the validity of logical arguments and identifying whether two statements are logically equivalent. A statement can be known as tautology if all the value for the proposition variable is true. If all the value for the proposition variable is false, it is called contradiction. Lastly, if all the variables values are both true and false, it is called contingency.
Argument and the rule of inference. Argument is a set of statements which have premises and conclusion. In argument, the last statement is called conclusion and the rest statement are called premises. The argument is is valid logic. Valid if logic implies to the conclusion. Following is an example of an argument. I will buy a motorcycle or a car. I won't buy a motorcycle. Therefore, I will buy a car. B, I will buy a motorcycle. Q, I will buy a car. The argument will be open bracket P disjunction Q close bracket conjunction negation P. The premise are as follow. Premise 1, P disjunction Q. Premise 2, negation P. So the conclusion is Q. Rule of inference are established logical template used to demonstrate the validity of an argument without needing to construct an exhaustive truth table for every scenario. These rules serve as the building block for mathematical proof and complex computer algorithm. Some of most common rules include modus ponens, modus tollens, and hypothetical syllogism. Modus ponens: if conditional statement P, implication Q, and its antecedent P are both true, then the consequent Q must be true. Modus tollens: if we know P implication Q is true but Q is false, negation Q, we can logically conclude that P must also be false, negation P. Hypothetical syllogism: this rule allows for transitive reasoning. If P implication Q and Q implication R is true, then P implication R is also true. We also have 12 rule of inference, but mostly used are 3: modus ponens, modus tollens, hypothetical syllogism that I just said. There is also others. There is disjunctive syllogism, addition, simplification, conjunction, contradiction, conditional proof, proof by case, constructive dilemma, and destructive dilemma.
Okay, Assalamualaikum. Now I will present about my part, that is chapter 3, the application of logic in real life. So, for the beginning, let's start with 3.1, the conditional and biconditional statement. For our first scenario, it is digital privacy and social media. So first, the original statement, P implies Q. If a user enables two-factor authentication, then their account security is enhanced. For the inverse statement, negation of P implies the negation of Q. If a user does not enable two-factor authentication, then their account security is not enhanced. And next one is converse. For converse, we will swap the two variables, that is P and Q. So now the statement will be, if the security is enhanced, then the user enabled two-factor authentication, as you can see right here. So for the next one, when we already swap the two, we will negate both of them, and that's what is contrapositive. So for the contrapositive statement, if the account security is not enhanced, then the user did not enable the two-factor authentication. Okay, so for the next one, let's head to the truth table. Okay, so now for 3.2, the truth table. Our real life situation this time is the University Scholarship Committee's rejection criterion. The committee states two different rules for disqualification. We want to determine if they are logical or identical. So our first statement, it is not the case that you are eligible if you have a high GPA, participate in sports, and perform volunteer work. So for the symbolic form, you can see right here. Okay, so for the statement 2, you do not have a high GPA, or you do not participate in sports, or you do not perform volunteer work. The symbolic form is as follows. Okay, so we have three variables in the truth table. The first one is P, student has a high GPA. The second one is Q, student participate in sports. And the last one is R, student perform volunteer work. So as you can see here, the truth table is as follows. We have our main three variable here, the two statements here. Wait, let me change that. The two statements here, and three negation of our original variables, and lastly the conclusion. So as you can see here, the conclusion for the truth table is Since the column for the first statement and the second statement result in identical truth value for all possible scenarios, the two statements are logical equivalent. This means the committee, two different ways of phrasing the disqualification rule mean the same thing. So on to the next one, that is 3.3, argument and rules of inference. So our scenario this time is smart home security logic. So we also have three variables. That is, the first one is P, the transaction amount exceeds RM1000. The second one is Q, the system requires a tag, that is transaction authorization code. And lastly is R, the transaction is flagged for manual review. So for the rules of inference, we have three premises. The first premises is if the transaction amount exceeds 1000, then the system requires a tag. For the symbolic form, it is P implies Q. For the second one, if the system requires a tag, then the system is flagged for manual review. The symbolic form is Q implies R. And for our third premises, the transaction amount exceeds 1000. So the symbolic form is only P this time. Okay, so for the steps, first we need to arrange them by premises. As you can see here, I already labeled each premises here. And so on to the next one, we will take the first premises and the second premises. So when we arrange them as is, we can see P implies Q is the premise 1 here, and the Q implies R is the second premise. So by using the rules of inference, the rule of hypothetical syllogism, we get that P implies R as our premise 4. Okay, so after we get our premise 4, we need to take our premise 4 and pair it with our premise 3. Okay, so as you can see, I have a typo here. Let me correct that. Okay, so now we have our premise 4 and premise 3. When we have arranged them like this, by using the rule of inference modus ponens, we get R. So the conclusion, R, the transaction is flagged for manual review. So the conclusion is the same as our premises, as our variable. The transaction is flagged for manual review. So the conclusion is the transaction is flagged for manual review. Okay, so now for the conclusion. In conclusion, the study of fundamentals of logic is essential for developing a structured approach to problem solving and critical thinking. Throughout this assignment, we have explored how conditional and biconditional statements form the basis of logical reasoning, how truth tables provide a visual method for verifying logical equivalence, and how rules of inference allow us to derive valid conclusions from a set of premises. By analyzing these concepts, it becomes clear that discrete mathematics is not merely an abstract academic subject, but a practical tool used to ensure consistency and accuracy in various fields. Furthermore, the application of these logical principles in real life scenarios, such as cybersecurity protocols, university eligibility rules, and automated banking system, demonstrates the indispensable role of logic in modern technology. Whether it is implying complex instructions using the Morgan's laws or validating security process through modus ponens, the ability to think logically ensures that system remains secure, fair, and efficient. As we continue our studies in MAT210, these foundation skills will serve as the groundwork for more advanced topics in computer science and mathematical analysis. So that's all for our presentation.